No? Okay, thank you. Well, I'm software engineer at Marmos. For whoever don't know, Marmos is an open source alternative to Slack. It's writing in Go, so if you want to take a look, just check it out, the source code in GitHub. Well, but I'm not here to talk about Marmos. I'm here to talk about the secret life of a Goroutine. Whenever I started investigating how the Goroutines works in the runtime, my idea in my head was that something like this: a caring mother taking care of her baby, so something nice and beautiful, right? The reality is not exactly like that. It's more like this: a necromancer raising the dead. So, and we will see why. But before that, I want to talk about the scheduler. I'm going to do a shallow introduction about the different pieces of the scheduler. It's not going to be deep because I want to talk more about the Goroutines itself. So one of the pieces of the scheduler is the processor, the P struct. The P struct is a virtual processor. It's a representation of our physical processor, and is when you say go mac procs, this is the struct that you are limiting. Is the number of processors that you are using. It has different statuses, can be idle, can be running, can be in a syscall. It has the current M, that is the current operating system thread that can be associated to the processor. It has a list, a queue of runnable Goroutines that are going to be executed eventually by this processor. A list of free Goroutines that are Goroutines that can be reused in the future. And other metadata. Again, this is a shallow introduction, so I'm not going to get too much into the details. If you see in the bottom right corner, you are going to see reference to the source code of the Go runtime. If you want to investigate more, just take the slides and go to that reference. It's about the 1.20 version of the Go compiler. So, yeah. Another thing is the M, another struct is the M, the machine representation is operating system thread abstraction. And it's going to have associated the current coroutine and the current P, current processor, and other metadata. Also, we have the scheduler. The scheduler is a kind of global place where some things are stored, but the main things that are stored in the scheduler is the idle M's, the idle P's, and a global queue of Goroutines to be executed, and a global global list of free Goroutines to be reused. And the Goroutines. A Goroutine in Go is mainly a stack, just a chunk of memory, 2 kilobytes of memory that are for storing the stack information. A program counter that is a pointer to the current executing instruction in assembly. The status, that is the current status of the Goroutine. We are going to see more about the statuses. The current M, the current operating system thread that is executing this Goroutine, if it's executing, and the wait reason. Whenever a Goroutine is in the status waiting, it has to have a wait reason. It's waiting for something. It's waiting for a reason. And we are going to see that reasons are relatively limited. So, okay, and again, other metadata. So this is the whole picture. You can see there some processors that each processor have its own queue of runnable Goroutines, Goroutines that are ready to run, free Goroutines. Every running Goroutine that you can see there is associated to a processor, to a operating system thread. You can have even operating system threads associated to a Goroutine without being associated to any processor. We are going to explain a bit that later. And then you have the scheduler where you have the global queue, the global free Goroutine list, and the list of idle processors and the idle machines. Also, as part of the global state of the runtime, you have all the M's, all the P's, and all the Goroutines in 3 lists that are the global state of the Go runtime. Okay, let's talk about the birth of a Goroutine. Here comes the metaphor about the zombies comes from here. Basically, whenever you try to create a Goroutine, what it's going to do is going to go to this free list of Goroutines that is not other thing than dead Goroutines. Goroutines that are already finished and are dead, are in the dead state, and take one from there and just populate the data and change it to runnable and schedule that in a processor. What happens if you don't have a dead Goroutine? Well, you create a new Goroutine in idle state, full of life, and you kill it, and then you convert that into runnable. So that is how it works. Let's see more in detail. Imagine that you have this running Goroutine that wants to spawn a new Goroutine. What it's going to do is pick this free Goroutine, this dead Goroutine, and populate it and change it into runnable state and add to the queue of the processor. Imagine that this one is the one that wants to create a new Goroutine. What it's going to do is go here to the scheduler, get the global list because my processor doesn't have any free Goroutines, so I'm going to go to the free Goroutines in the global list of the scheduler. I'm going to pick a chunk of them and add to the processor, and then I'm going to pick this one and do the same. And again, if I want to do that, but there's nothing in the global queue and there's nothing in the local queue, in the local free list, sorry, it's going to create a brand new Goroutine in idle state. It's going to kill it, and it's going to add to the queue. So, okay, let's talk about the life of a Goroutine. The life of a Goroutine, whenever a Goroutine is alive, it can be in these states. These are the states that exist. Apart from dead and idle, these are the state that exists. So a Goroutine start normally run in runnable mode and can be running, from running can go to waiting, from waiting can go to runnable again, from running can go to preempted, can go to copy stack and back, things like that. So let's talk about each of these transitions. Runnable to running. Well, when somebody calls the scheduler is going to try to find a Goroutine. Well, first of all, Goroutines is a cooperative, follows a cooperative approach. So whenever somebody calls the scheduler, it's a running Goroutine who calls the scheduler. So a running Goroutine calls the scheduler, that means I'm giving up whatever I'm doing and I want the scheduler to schedule something else. So when the scheduler runs, try to find a runnable Goroutine. What it's going to do is try to search in the processor queue and see if there's any Goroutine, any runnable Goroutine. If not, it's going to go to the global queue. If there's nothing, it's going to the net pool, that is another part of the runtime that is taking care of all the network-related traffic, and is going to check if some network operation have finished, and if that's the case, it's going to take one of that Goroutines that were waiting for the net pool to finish and move that to runnable. And if that's not possible, it's going to try to steal work from other processors. And finally, if there's nothing to do, it's going to try to help the garbage collector. Whenever it finds a Goroutine, it's going to assign to that Goroutine the M, the current, the operating system thread to execute that. It's going to mark as running, and it's going to start executing the code. From running to waiting, again, a Goroutine is a cooperative, that follows a cooperative approach. So it's the Goroutine who decides when to stop. There's no, the scheduler doesn't stop Goroutines or things like that. It's the Goroutine who decides to stop and park itself. So park itself means that it's going to set the status to waiting, and it's going to remove the current M. It's going to detach from the M, the current operating system thread, and it's going to call the scheduler to find another Goroutine to execute. What means waiting? This is the list of waiting reasons that you can have, and this is the whole list. It's in the source code, and there's nothing else. There's no other reason to wait for a Goroutine to wait. To summarize, basically is garbage collector reasons, mutex, semaphore, channels, flip, IO. There's others like select and things like that. But in general, the main reasons that you are going to find are that. Okay, let's talk about running to syscall and running or runnable again. Whenever we call any syscall to the operating system, it's going to execute two functions. It's going to call enter syscall, the syscall itself, and exit syscall. The enter syscall is going to save the the program counter and the stack pointer of the Goroutine. It's going to change the status to syscall, that is that frozen state. And it's going to detach the M and the P from the Goroutine and set the status of the syscall to P. Then it's going to execute the syscall. And whenever the syscall exits, if the syscall was fast, it's going to move back to running again. So it's going to be able to keep running keep running in the same process without giving the control to another Goroutine. But if the syscall is slow or blocking, it's going to put the it's going to wait until that happens, until the syscall finish. But when the syscall finish, it's going to move that into runnable and detach from the M and stop the M that was used for that and call the scheduler again. Okay, running to copy a stack and back. The Goroutines have this stack, this chunk of memory of 2 kilobytes that basically can be enough sometimes, but maybe it's not enough. Whenever you call a function, the compiler already knows that how much memory is needed for the stack. So whenever you run a function, it's going to see that memory that is needed for the stack, check if the Goroutine have enough space in the stack, and if that's the case, if that's not the case, it's going to do a stack grow. And that starts with moving the Goroutine from running status to copy stack status. Then it's going to reserve a chunk of memory. Normally, is the double of the existing stack. Then it's going to change the pointers and all that stuff and change back to running the Goroutine. And that is how the stack grows in a Goroutine. Waiting to runnable. Whenever you have a waiting Goroutine, there's multiple ways of getting a Goroutine runnable again. The first thing is GoReady. GoReady is a function that other Goroutines calls when needs to get a waiting Goroutine ready to run again. Normally, this is used inside channels, inside semaphores, and things like that to re-enable that Goroutines that were waiting for something, for some data to come in the channel or something like that. When you call GoReady, it changes the status to runnable and add to the processor queue and try to get the P again running, the processor running. Okay, waiting to runnable. Another way of moving from waiting to runnable is reactivating a list of Goroutines. That can happen, for example, as part of the garbage collector. When the garbage collector finished his job, sometimes reactivates all the Goroutines that were waiting because the garbage collector, and basically mark all them as runnable again and wake up all the P's needed and add them to all the queues wherever is needed. Okay, another way is sometimes you don't need to wait. Sometimes you change to waiting, but you realize that you need, the The runtime realizes that doesn't need to wait and is going to change to runnable again, and is going to change to running and execute back, go back to executing the Goroutine again. So that basically again is this kind of things that avoids switching to another Goroutine. Another place where you can change from waiting to runnable is whenever you are trying to find a Goroutine. One of the things that it does is try to check the netpool, and the netpool have waiting Goroutines that are waiting for the netpool to finish. But whenever it finishes, it doesn't go directly and make the Goroutine runnable again right away. So the Goroutine can find, the scheduler can find that Goroutine in waiting state, change that to runnable, and queue that. Also, can happen as part of the wake up of certain tasks for certain Goroutines for mark assist, for helping the garbage collector. Okay, running to preempt and waiting and runnable. Okay. Golang have preemption, but the preemption works in a way that basically what it does is mark the Goroutine as preempt, and the Goroutine is going to find a safe point to preempt itself, and is going to change the status to preempt in that point. The next garbage collector changed that preempt to waiting, then it's going to do all the scan process that it's going to do. This is going to be in the mark phase of the compiler. So it's going to of the garbage collector. So it's going to change to waiting, do all the scan, all the garbage collector and scan that needs to be done, change to runnable, and queue it back again to one processor. And that's it. That's the life cycle of a Goroutine. This is all the different things that can happen. But I'm going to talk about some examples. I'm going to talk about channels. Imagine that you have this running Goroutine that wants to send data to a channel. It's not a buffered channel. Nobody is reading data from that channel. So it's going to park itself. It's going to say, hi, I have to wait. It's going to get in a list of waiting Goroutines of the channel. And another running Goroutine comes and tries to read the data. So it's going to go there and read the data from the waiting Goroutine. It's not going to ask the other Goroutine to do anything. It's going to go directly to the memory, to the stack portion of the memory of the other Goroutine, read the data, and then it's going to mark that Goroutine as ready. So the other Goroutine is not doing anything. So as soon as the Goroutine marked that as ready, the other Goroutine is now runnable and is in a queue, and the running Goroutine that was reading the data keeps going. So this is the whole picture. And a wait group. Another example is the wait group. This running Goroutine creates a wait group, add 3 elements to that wait group, and spawn 3 Goroutines. Then it calls wait. Whenever it calls wait, maybe some Goroutines are running, maybe not. Maybe all of them are running, doesn't matter. So whenever it calls wait, the Goroutines start waiting, and the Goroutines that were spawned are there running, doing his job, and some of them finished, all that stuff. It's going to call done to the wait group. And the last one is going to call done to the wait group. That last done is going to end up generating, the semaphore inside the wait group is going to end up green, and that is going to trigger a ready change to a ready call to the Goroutine that was waiting. So the final state is that the last Goroutine after doing that dies, and the Goroutine that was waiting is now runnable and queued in any processor. So that's the example of the wait group and the death of a Goroutine. Whenever a Goroutine finishes the work, change the state to dead, and basically set most of the values, the Goroutine values, to 0, disconnect the Goroutine from the operating system thread, and add the Goroutine to the free list of the processor, and call the scheduler to find another runnable Goroutine to execute. So now this image here should make more sense, should be more obvious what's going on. And this here is all the states of the whole life of a Goroutine. Okay, let's summarize a bit. One thing is the illustration of this talk are Creative Commons by, so everybody can use it. So feel free to pick them and use wherever you want. They are created by Laura Pareja. The QR code there is the link directly to the illustrations. Okay, what is missing? I haven't talked about the garbage collector deeply. I haven't talked about the net pool deeply. I haven't talked about SIGO at all. I haven't talked about Mark Assist deeply. And I haven't talked about Sysmon. All that things are related to Goroutines. They play an interesting role in Goroutines, but I have to cover a lot of field, and it's not possible to cover everything. Some references, well, the main reference for me is the Go source code. As I said, at the bottom right corner of a lot of slides, you are going to find the places where you have to find, where you have the information or the source code of the slides. Well, the source code that refers the slides, basically. And then also there's an interesting talk that is called Illustrated Tales of Goroutine Runtime Scheduler. And also there's a interesting set of blog posts from Arden Labs about scheduling in Go. So if you are interested on the scheduler and all that stuff, go there, it's pretty cool. Okay. I hope after this talk, you understand better what is the real behavior of the Goroutines and understand the cooperative nature of it. Also, and more importantly, I want to encourage you with all this information here and all the pointers in the slides to go there and explore the source code of the Go runtime and see how it works. Because depending on a combination of your passion about learning and your taste about movies, this can be more exciting than a zombie movie. So, thank you.
Hi. Yeah, I'm not sure if you explored this earlier, but do we know why it goes from idle to dead and then not just idle to running? There must be a reason, I guess.
Yeah, there's a reason. The statuses is an enumerated value, and there is the 0 value of the status is idle. There is and it's not used anywhere in the runtime except when you create that. So you create the Goroutine with 0 value for the status, and that Goroutine with 0 value is idle. And then you move that to dead. I think that's the reason, basically. But it's a funny thing to make a metaphor around that. So.
Thank you for the presentation. That was really good. I was wondering if you obviously have deep knowledge about this, if this knowledge in your day-to-day coding has made you more efficient using Goroutines, because one of the Go kind of advantages, I guess, is that they abstract all of that for us, right? So we just call Go something, let it do its thing. Do you think knowing this in depth would help us make our programs more efficient, maybe?
Well, Well, first of all, I'm not an expert of this. I work as a API, a full stack developer, actually. So part of my time is writing front-end in JavaScript and things like that. And part of my time is writing APIs. So I'm not doing system engineering or something like that. I don't write a highly optimized performance code. This is more about my curiosity about how it works. It is basically a foundation of how things work. I was curious about how when the Goroutine stops, when the Goroutine starts, when the Goroutine waits. That was what leads me to start investigating the Goroutine, because I think it's something that is not so obvious. You can spawn Goroutines like crazy and doesn't matter because Go is great and all that stuff. But the reality is I want to know if I spawn a Goroutine, it's going to execute that directly. What's going to execute first? The Goroutine that I spawn or the Goroutine that is calling that Goroutine? All that stuff or what happens when it ends? If I create hundreds of Goroutines or thousands of Goroutines, why is so performant? Because you are not creating them, actually. You are reusing a lot of them, for example. There's a lot of information there that is interesting. I don't use it in my daily work, but I think it's a great foundation for better understanding of channels, of weight groups, and things like that.
Thank you.
Cool. That's good on time. Thank you very much.
Okay. Well, one thing, I bring some stickers. Some of them are from my company, Maramos, but I made some special stickers for this talk. So if you want to take them, are in the table back there. So, thank you.